this was your homework from last time, which was basically just repeating what we did using a loop with recursion. So in this specific case, making exponentiation, well, raising x to the power of y using a method that's only based on recursion instead of using a loop. So repeated multiplication using recursion. And the way to solve this, well, first let's have a look at what the code should actually do. What we did before is we multiplied x by x and then stored it in some variable, and then we repeated this step over and over and over again. So we'd always have start off with maybe t equals x and then t times equals x, so multiply x into it and then times equal x and then times equals x and so on, y times. Actually, I would start off with a t equals 1, like that. And what this effectively does is turn this into repeated. Let me write that out properly. Times like that. Repeated multiplication. We did this using a loop. But of course, recursion is very similar. Think about recursion. We call a method that will execute some code inside these curly brackets, similar to a loop that also has some header for what type of loop and curly brackets for the code block that contains what code we want to execute. And the loop then automatically jumps back up and runs the same code again. And we can achieve the same with a method by just having at the bottom of our code a method call that calls the same method again. So we can replicate a loop very easily with a method. The detail is what matters though. Because if the loop would just continuously call itself, or if the method would constantly call itself, we would have endless recursion, which has some problems. Two specifically. The first one, of course, if it's constantly calling itself, no matter what, it will never finish. The method will call itself, which will call itself, which will call itself, and we will never get a result because it's constantly just calling itself, calling itself, calling itself. We would never get anything really done. The second has to do with memory, which is the big topic we're gonna tackle today. So for recursion, you always have to make sure that there's some point where the loop ends, something that comes naturally with actual loop statements, because you always have to include a condition for when the code should repeat or not. But for recursion, you have to manually add code that will automatically exit the loop, so to speak. So let's just remove all this. Let's try the method. What do I call that? With a oh. Alright, so I already gave you the signature. And x and y. So the condition is something I'm gonna put up first before I call the loop body, kind of. And the condition should be that we don't need to make any more multiplications. Keep in mind, we have the arguments x and y, which was for x to the power of y. What did we do in the loop? We had a variable that was constantly counting down from y to 0, and as long as it was greater than 0, we would multiply x into a variable, but as soon as we reached 0 with the counting variable, we would stop. In our case, we can use y as this counting variable and just use that as an indication that we should stop. But this method should always return a value. That's what we defined. It will return a long. So we can't just stop. We have to return the result of something. So what we do is we define some existing results for specific values of x and y. Like values where we know this is going to be true, no matter what. Constant values that we can return. For example, if x equals 0, simple example, we can just make a return statement here, return, and we can just return 0. 0 to the power of something is 0, right? Or we can check for equals 1 and then just return a 1. Maybe more in general, can simplify this into if it's less than 2. We're assuming that no negative numbers will be input. We can just return x. And we can extend this condition because if y, our counting variables, or power here, is equal to 1, we will also directly return the value of x, whatever that is. 2 to the power of 1 is still just 2. So we covered that case. Now let's also take care of the case for y equals 0, just in case someone calls the method for y equals 0 directly. In that case we can just, if y equals 0, return 1. Something to the power of 0 is 1. Of course, in this case we would have maybe a special case for 0 to the power of 0, which for our situation would first hit this condition and therefore would be equal to 0 with our algorithm. I think the official definition was that this should be a 1, so we have to actually move these two conditions. Let's move it down. That's what did I do? What did I do? Let's move them both down. See, that was that condition like that. And let's move this back up. That's more like it. Alright, so those cases are done. Again, we're assuming no negative values, even though technically these would allow negative values to go into the method. So, just to be sure, maybe... No, let's actually ignore that for now. Anything raised to the power of 0 would now return 1. And if we raise something to the power of 1, or if we raise 0 or 1 to the power of something, we just return x. So the value itself. These are our conditions. And they will result in us breaking the loop, kind of, because we just return a fixed value, there is no recursion, we don't call the method again. The special situation here is, of course, that we can return different values depending on what input we have. Whereas in a loop, we would always have the initial value that we set in our temporary variable. And now we come to the recursion part. we can now use this method in another return statement. Because what is x to the power of 3? Well, it's x to the power of 2 times, that looks like a plus, let's do the times x, right? And x to the power of 2 is the same as x times x. That times x. So x to the power of y is the same as x to the power of y minus 1 times x. Let's clear this out. And the method is done. If we raise something to the power of 0, this method will give us a 1. If we raise something to the power of 1, or if we raise 0 or 1 to the power of something, we return, well, that value that we tried to raise to a power. And if it's neither of these cases, we will first calculate what if we raised x to the power of 1 less than the current power. And then we multiply it by x to raise it to, well, y directly. So if we have x equals 3 and y equals 2, well, this condition would not apply. These conditions would also result in a false, making this entirely false. And then we calculate for 3 and 1 times 3. And if we call 3 and 1, if that's when that's evaluated, not if, well, we go back in here. Y is not 0, so this one is skipped. X is not less than 2, but y is now exactly 1, so we return 3. So this entire thing now gets evaluated and turns into just a 3, which is multiplied by 3, which is then turned into a 9 and returned. So output is 3. It's very simple, really. Like, the only complicated part of recursion is keeping track of what are your conditions that break the chain of repetition. Where do you jump out of the recursion? Where do you stop? This is also sometimes called, or usually called, the anchor, because it's your breaking point, your stopping point. This is how you make sure that you will come to a halt at some point. That's why they are usually written first, and most of the time it's something where you have a variable counting down until it hits a low value. Another famous example, like, just a side note, let's do it like this. That's also a classic for programming lessons, the Fibonacci numbers. If we try to generate the Fibonacci number, the the Fibonacci number at position x in the Fibonacci sequence. Well, we just return. This is not the full solution, of course. You see the mistake in a moment, but basically it's just the Fibonacci number for x minus 1 plus the Fibonacci number for x minus 2. Okay, when the numbers were 1, 1, 2, 3, 5, 8, 13, 21, and so on. Always 2 digits prior, summed up, get the next one. So to get this Fibonacci number, you just calculate the one step before plus the one 2 steps before. Fibonacci number x minus 1 plus Fibonacci number from x minus 2 gets you Fibonacci number from x. Problem is, of course, now x will just get decreased constantly until we hit an underflow, and then we start with the big ones again, and yeah, that's why we can't leave this as is and have to add the anchor that prevents us from just running this code ad infinitum. And simple method, that is if example of x less than 2. Well, depends on how we want to count. Do we start with a 0 here? Is that 0th place or is that first place? Let's assume that's 0th number. Then this would work. Return 1. So if we look for 0 or 1, we will just get a 1. But if we look for Fibonacci of 2, we would hit this condition is false, and we would check for Fibonacci 1 and Fibonacci 0, which both just result in a 1, and they get ended up to a 2, which is correct. And if we check for the third one, we would check for Fibonacci of 2, which we just did, which itself will call Fibonacci and effectively just hit this return statement at some point. And it will add the first or ones Fibonacci number, at least in our system, which will also just directly return 1. This is a side note. This up here is one potential solution for your homework. Anyway. What is the other problem with recursion, if you are not careful enough? I already mentioned that we have this endless repetition. It never halts. You just constantly call the method and your actual program never progresses because you're constantly just trying to call a method which calls itself forever. That would work on a theoretically perfect computer with infinite memory, but not on a real computer which has very finite memory. Because every time you call a method, you need some extra space to store the data. Let's make a simple method here. And let's call it big S, which gets an int A for a change, not an X. By the way, I apologize for the sound quality. I'm not sure how well or, well, not well it gets through. My office is undergoing some heavy renovations and there is 0 soundproofing now in this room. Just bare walls and nothing in between. No interior whatsoever, except for this lonely desk I'm sitting on right now. In this, and what we're gonna do is, if A is less than 1, we return 0, and otherwise we return big S of A minus 1 plus A. Pretty simple. This is a recursion that will simply generate us the sum of all numbers up to a certain number. So A equals 0 will just give us 0. A equals 1 will give us the sum for 0, which was 0, plus 1, so it's 1. And for 2 it will give us the sum for 1, which was 1, plus 2, which is 3. So 0, 0, A equals 1, 1, a equals 2, 3, a equals 3, 6, and so on. Think of it like a simpler Fibonacci sequence. Just summing up all the numbers. I told you that whenever you call a method, you get a unique table for all the variables. Let's just draw this simple table for now. So we call the method, and initially we have the declaration for the value for a, the argument, which gets some value that we don't know now, but someone who calls this method will give us the value we can put in here to initialize a. And there are no further variables inside this code, so that's the only one we call. I also told you that there is some hidden data you don't get to see, especially the return address that lets us jump to the previous position in our code when we hit return. That's what we need for, and it's a hidden value, but it's also in here, which we're not going to talk about that specifically, but just know that there is return value or return address. Return address. So whenever we call this method, we will need space for two, or at least for now, we assume it's only two variables, so to speak, which both have a fixed length they need in memory. And if I have a recursive method, especially then, you can quickly fill up your memory with many of these tables. Because when I call this method the first time, we need space for these two variables, this table in memory. But before this method even finishes, we call this same method again and need one additional table with two values. And then we call it another time. And we need another table with two more values. So as long as you have a recursive method, you will get constantly new tables which have to store additional data. So in our case, two variables at least. That means you can quickly fill up the memory. And the specific memory we're filling up, that we're running out of space for, is called the stack. I arranged these tables below each other right now, and that's actually not far from the truth. Every method you define in C# has a specific size it will need on the stack. It's just another form of saying we know exactly how many variables we're gonna need at most at the same time. We will know exactly how many rows this table will have at most. It's not how many rows will be filled at any point, because that can change. Especially if you something like internal, like if we make just curly bracket here and b 0. I can just add a code block in here, right? Remember, scope. And once I hit this, I suddenly have an int b 0. So I need 3 rows. But once we hit this return down here, this entire row is removed. Go back. Good. And we only need 2 active rows now, but we did at some point need 3 rows. So this code would be specified as we need space for 3 variables. And because we also know what type of variables, well, at least kind of, we know how much space exactly this will take in memory. But just for now, just focus on the number of rows. That's all that matters for us right now. We know this method will need space for 3 individual rows. That means every time we call this method, we need to reserve space in memory for 3 rows data. Because we know this is a continuous flow for the code from one statement that has to wait for the next call before it can continue, we know that the first call of this method s will wait for the second call, which will wait for the third call. The tables for the first call, or the table for the first call, will need to remain as long as the table for the second call remains. Because this first table is just for the first call of the method. As long as the first call isn't finished, this table has to remain. And this first call will not finish until the second call has finished. It will actually remain a bit longer, but as long as the second call isn't finished, the first call is definitely not finished. So as long as the second table remains, we will definitely need the first table. And same for the third table. That will definitely indicate that the second table is still needed, which indicates that the first table is still needed. But once the call is done, this table can be removed. These two tables still need to be there. We need to keep them until the second call is resolved as well, at which point we can drop this table. Will you clear out? Thank you. Until we're only left with this table. And once this call is done, we can go back to whoever called us in the first place, and this table can be dropped. But you always build up on top of each other. First table for the first call, and a second table for the second call, third table, and then only 2 tables, 1 table, so on. You never have the situation where you have 1 table here, second table, third table, and we remove the second one. This situation can never happen. We will always have something in here. And in memory, which is just one large continuous chunk of memory. Remember our initial CPU design? Everything is just one large chunk of memory. Some parts of that, maybe these first 2 or first 3, that's where our program is. I mean, our program will need more space than this, but just an example. This is where the program code is, all the instructions that we're actually executing. But the variables, the temporary data we use that are changed by this program code, they are residing in the space afterwards here. And that's our stack. The stack is just one chunk in our memory that's reserved just for data we want to add and manipulate. Not data that's existing already. Like if you have any constants in your code, like there's 0 here or there's 1 here, those are values inside the program because you ship them out with your program. That's part of the memory that we always fill before we start running the program. But when we actually run the code, we suddenly need space for an A. And so we reserve. Maybe let's make an equation here. Let's remove this one, just go back to the normal code. We need space for the A and for the return address. So first call. We need these 2 addresses. They're now reserved. That means this one is now the next free space. So when we make the next call, we make second call. We block this space. And then make the third call maybe. So we take these spaces. And always we have one space on the top that's free for us to use for the next method call. Every time you call any method, we just go to the next spot on our stack, basically the first free address, We just go down the entire stack. And that's where we're going to put the return address that we're going to jump back, which is going to be needed by any method. And maybe we include some additional data like where the method is from, what type of method this is, maybe or maybe not. And of course we need to reserve space in here that we're going to use for the method itself. Keep in mind, it might be that we make a method call like like that before we finish the method, right? And we might have another int c equals b plus 1, and then return c like that. Doesn't make much sense, but this is also a possible scenario. Likely scenario for any method. Not necessarily for recursive methods, but maybe this is as another method, entirely separate from this one. Could be the same, of course. And in that case, not all the space we reserved for the method call is going to be used. So maybe use return address. Return address, then some variables. And then maybe there's some open unused space. That is reserved for our method. That's not used right now, but might be used later. And then this is where the next method comes in. Another return address. And maybe this one uses a bit more of the memory already. And has some more free space. Actually, the way I indicated right now, it looks like they're all the same size. They are not the same size. Some might be actually smaller. This might also be something that's not using the memory exactly. But this is all stack. We call a method, we reserve some space on the stack that's only for one method. Could be the same method, just another call for the same method. Call 1, call 2. This might be entirely different method. This might be a different one. And so on. And not all the space we reserved will be used immediately, but we know that we might need this space at some point during execution of this method. So it's still reserved, even if it's unused. It's equivalent of our tables that we used before. Just imagine these are just straight up copied into memory, and only a few of those spaces are used, and the others are unused so far but might be needed later. Just imagine these are stacked on top of each other in memory. Computer knows, hey, this is where one method starts and another one ends. So for our usual method of iterating through or going through a method, we can just assume these are individual tables that are completely separate from another. The computer will mush them all together in one long piece of memory. Call 1. And that's the simple strategy the computer uses to reserve space when it needs it, but then freeze it back up once the method is done and we don't need it anymore. Right? The idea is that we only occupy space in memory when we actually need it, because it's limited. The more our program just reserves space in memory for nothing, the less space is available for other tasks on the computer. And sometimes those tasks are even coming from our own program. There's, however, a way you can reduce this amount of memory. Let's just do the same method again. But we'll alter this time. So this was our int. Let's just first rewrite the same method, int a. If it's less than 1, return 0, and otherwise return s of a minus 1 plus a. This was the original method, and that means every time we call it, we will have to reserve space for this a. That's only used to check a condition and make some simple operations here. We have one subtraction, one addition, and then we can drop it again. But every time we call this method, it will call this method again, and maybe this one will call it again, and again, and again, and again. And if we have something really large, like maybe we start with s 1 million, that means this method will call itself 1,000,000 times. First method starts with 1,000,000, we'll call the second method, make the second call with 999,999, which then we'll call the method again with 999,998. And continuously like that 1,000,000 times. So we have 1,000,000 tables in memory that will completely fill up the entire stack, the entire memory that's available for our program, and we'll not even get anything done. Now 1,000,000 times is actually not that much. Depends on the PC you have, but it could actually, depending on your settings and everything, it could actually still remain stable, could actually work, but it's probable that at some point you will get a so-called stack overflow. And just letting that name sink in, because you probably heard it somewhere else already if you're starting to program. That's where the name comes from. Stack overflow is just our memory runs out. We don't have any more space to store our data. We can't call any more methods, even though we want to call another method. If we want to use more memory, there's simply nothing available anymore. And we get an error. The computer says, no, I don't have any more space for you. I can't continue with the program. It's just not possible on this machine. We simply do not have enough memory available anymore. There are strategies around this, and especially for recursive methods, a lot of that has to do with how you structure it. For example, the order in which you do operations and call methods. That's very important. But in this case, there's a way simpler method of handling everything. Even if I call the method 1,000,000 times, if I somehow avoid every single method call having to reserve space for this a, that would also mean that I save space for 1,000,000 integers, which is quite a lot. Well, not that much, but it's still a lot. And the way we can do that is by essentially telling the system to ignore the boundaries that are here. Usually, this is one method call, this is another method call, this is one method call, and these methods only know what's in their own table. We only know what's inside these, between these boundaries. nothing more. We can, however, give them the information that there is another table, another part in our memory that has the necessary data. We can, instead of giving the method the instruction, hey, start with this integer, start with the integer at a very specific position in memory, not in your own stack. And we can do that by using the keyword ref. Int a. And now we have to restructure our code a bit. Let's see how that would look from normal code if we write it out. For example, I might have an int b equals 3. And I want to call, usually what I would do is in sum equals big as b. And that would store 6 in the variable sum. With this structure, however, what I can do... Did you update? Okay. Actually, well, we need to adjust it anyway. Let's move this back up here and sum. Actually, that was the wrong choice. I should have kept it int a. That was actually correct. Forgot. That was a different program that I had in mind. This int a can stay, but we do add another. Now I'm mixing two different programs. That's why it doesn't work. Ah, my bad. That's my bad. Okay, so this is not actually saving us memory. This is just to demonstrate the possibility, but in my specific case it's not helping because I chose the simple sum method. Why did I pick the sum again? Because I wanted to show the stack and wanted to have it simple and didn't want to bother writing out the full map. Yeah. Okay, now I'm getting burned for that. Alright. Forget the performance. This one is not that much worse. It's just demonstrating, however, how you can do everything a bit differently. Actually, no, let's call it specifically B, because it demonstrates something. So we can now call S B ref sum. We have to change this code, of course. But we'll get to that in a minute. Actually, let's remove that. Make the brackets down here. This little keyword ref that we have to include both when we call the method and when we declare the method, when we write out the signature. This tells the computer that in this case we are not actually declaring a new variable b in here in the table. Again, usually you would have the int a, which would then get some value when we call the method, and an int b, which is declared in here and then would get filled, initialized with a value when we call the method. But in this case, this is a ref. This means that we're not actually declaring any variable here. Well, we kind of do, but only in the sense that this code knows there is a b, but there is nothing really in our table. It's like the code continues as if there was an entry. here in this same table, but our actual table in memory, when we look at the stack, has only the A. Where's this B coming from then? Well, it's declared here, right before we even start the first call. If we look at the memory, let's make the first table. Let's make the memory a bit bigger. Let's just assume this is the main memory, all of it. It just continuous number of stacks. It's just one stack, continuous chunk of memory, which contains all the tables. We need an int b, which is 3. And we have an int sum. Actually, let's initialize that with a 0, like that. Like this. And this part is our original code. And then the call for S will only reserve space for B, or specifically for A, which will get the value of B, but that's it. This mystery variable B that we sort of declared in our method, but don't actually add because it has the ref keyword, is actually a reference to this variable we've declared in this entirely different table. So it's like there is actually a variable B that is tied to this memory address. Usually this int A has its own memory address independent from this int B, which was here in the method call. We gave the value for B, but B is in memory at a different address than this A for the method call. Entirely different positions in memory with their own independent addresses. But because we use the ref keyword, we're telling the system, don't take this value and pass it on to a new variable B. Pretend that what we know here in this code as sum is the same as this int B. Just pretend you have an int B, which just happens to be located in the same address as this sum. So when we use B in this code, if we were to set B equals 1, we would go into our table for the method and we would set B to 1 like usual, but because this is a ref, we're not really addressing a unique variable B that only exists here. We're actually changing the value in this memory address. We're actually changing this to a 1. In the table for the first code, we're breaking the boundary. Alright, so ref lets us give the computer a hint that we don't want extra space for a unique, isolated variable. We want to use an existing variable, the exact same memory address, the exact same position in memory as this variable. We wish to just use that. And to make sure that both sides agree, both the method itself knows that we're referencing a memory address that's not part of my table, and the caller knows that this method will change values in my table. Let's both need to actually use the keyword ref. So as you as a programmer know exactly, this method will change this variable. It will change my table. And this method knows I'm changing someone else's variable, not my own. Also, specifically for the method, this means that B will have a value. So technically it's not just declared, it's already initialized. Unlike A, which will only get initialized once we call the method. Because this is referencing an existing variable that's already initialized before in another code, another table. This doesn't need to be initialized anymore, it's just a finished variable with everything. But that's not really relevant for anything, it's just side note. So how can we use this? We can now remove this in front. We make this a void method now. We don't need to return value. We're just going to change the existing value. And we're initializing here with a 0. And so if a is less than 1, we're just going to not do anything. Similar to before, just we don't return a value, we just don't do anything. However, if a is greater, we can first add, let's use the short version, a to b. So we add our current value for a to the sum, and then we call s again with an a minus 1. Yep, forgot the second argument, a minus 1, and ref b. Same as down here, we have to include the ref to make sure that this method knows, well, that we know this method will get a reference to this memory address and not the actual value of b for a new variable. And in this case, the b we pass on is not even our own variable, it's just something we got from someone else. So this code will call the method and will tell us use my memory address. And this method then will pass on this memory address to someone else. It's like we're passing on the address instead of the value. For a, we're just giving the value. Here we start the method, we start a method call, and when the method is called, we initialize variables with a value that's equal to the value we have in here. But it's an entirely separate integer a, its own table in memory. But again, with an implied declaration for an integer b, which is actually referencing this memory address up here. The same address is passed on to the second call of the method. And so this method will now check if a is less than 1. If not, it will just add our current value for a to the sum, which we know as sum down here and as a b up here. And it will call the method again with 1a less. Alright. And now we can go a step further. Now we can actually make that ref2. Ref int a, ref int, oh, let's remove this, get some space, ref int b, like that. And that means we now are referencing our variable b in here. Always forget the e. Ref b, ref sum, like that. And now we don't even have that a anymore. We still have other values in here. I'm just leaving that empty. We still have the return address. That still needs some space in memory. So that's why there's still empty block in here. That's also something we need in here actually, right? Every method has it. Every piece of code has it automatically, no matter what we do. But we don't need the extra space for the A for every call. That also means we need to change this code a bit. If A is less than 1, we return, that stays. We can still increment B by A, so we add B to sum, that stays. This method call can be changed though. We're now decrementing A. And I'm gonna squish this a bit. Ref A, ref B, like that. And then pass on the reference, the address for A, which was originally this variable B, and the reference for B, which was originally this variable sum. And we call the method again. So we do need to add the extra space in memory for the return address and some basic infrastructure code, which is always present for every method call, but we lose the overhead of having additional integer A's, which just aren't needed here. Of course, this means we have to present, for example, an initialized value for sum that we can pass on. And we have to make sure that B is properly initialized with a variable that we pass on. We can't make it static S5, for example, anymore, which we could do with our first program. The initial one could be just int C equals S5, like that. That was our original program. This would work. We could just use a constant value and call the method because we only cared about the value. The original program would just take the value give it and put that in its own unique variable, which it has declared already and would initialize then. With it, it would have reserved space for it on its own. But because we're using references, it's not reserving any more space in memory. We have to do it for the program beforehand, and then can reference that. But this is a way we can restructure something like recursion, for example, to be a bit more efficient. And we use it for a lot of other things. Because method signatures, we always have a return type or void, and we always have optional parameters. The key difference is we have one return type, we have optional parameters, arguments. I should probably stick to one of the two. Let's use arguments. We can have multiple arguments, but only one return value. And yeah, there are ways you can get around this too, with a bit of trickery that we'll get to next time. But generally, a method gets multiple values, but only gives you one value back. And with something like ref, you have a way to work around that. Because you can just add additional variables here with a ref, and that way you give the method an option to store additional values in places that you specified beforehand. So instead of forcing the method to put everything in the return statement, which is limited to one value, you can give it additional places it can dump data into, so you have kind of like several return values. You can cheat the system a bit. Not always the best choice, because it can make your code a bit more harder to read, but there are certain patterns that are very common and easy understood. And one of the most common has to do with something very similar to the ref, which is, let's make an example method. Yeah, let's do that. That's simple enough. And div and A and B. And what this method does is nothing more than return the R, return A divided by B, like that. Very simple method, right? I mean, that's simply just one operation. We did it the hard way now with a method, which is not really necessary, usually. But simple enough. This method has an issue. If I were to call this, let's move this further down. Let's maybe do on here maybe. And x equals 10 and y equals 2 and z equals div x y, like that. It would just call the method using the values 10 and 2. It would initialize the table with variables int a and int b, which are set to 10 and 2 respectively. It would calculate a divided by b, which is a 5, and it would then return to where we called the method and evaluate this to the 5, the value we returned. And then we would assign the value 5 to the variable z. What if this value is a 0? That would not work. We can't divide by 0. This code would simply run into an error and the computer would crash your program, because it cannot continue operation. There's no code that tells us what to do in this case, because it only knows that if I'm hitting a division with a 0, that's not defined. I don't know what to do then. And it will just throw an error. There are ways you can catch this specific error, of course. That's advanced topic, error handling, which will come quite a bit later. There is a way around this though. We know we can use an if to check for a certain condition and react to that. So we could use an if to check for is y, or is the second argument for our method 0? And if so, do something else, don't make the division. Do something that we specify so the computer knows how to handle the case of we divide by 0. But if possible, we don't want to write the code in here. I don't want to write an if case every time I call the div method. The whole point of this being a method is that all the additional code is in this method once, and I can just reuse it all the time. But if I just include it in here, well then I can return an int maybe. That's just 0 if I divide by 0, but that's not the correct value, right? Because if you get a division with a equals 0, it will return 0 normally. That's the correct result. But if you make a division where b equals 0, we might return 0, but it's false. Like, that's not the actual value, it's just we didn't have anything else we could return. We need some way of returning two values. We need the result if it worked, but we also need the information that the division was possible, it worked. We didn't divide by 0. And we could do that with a ref, sure. But there's a more common way to do this with an out. Let's rewrite this a bit. We'll get to that part later. First, we have this out, and let's call it D. Like that. And when we call it, let's remove this part for now. We also have to add the out. And this is a bit different. Like that. The out is very similar to the ref keyword we saw before. But the out is focused on just giving values out. It's dedicated to the whole, we're using the addresses to give a method more opportunities to return values. Additional values, except besides the actual return value. With a ref, we could have a value that exists outside the code, outside our method, be changed by the method. So this code is a bit unsafe in that our variables here get changed by the method in ways we do not immediately understand. So this could actually break your code in some way. So you have to be very careful with the refs. You have to know what the method does and if it's the right choice to do so. With an out, however, well, the only one with access to the variable directly is the method. Our method will determine what value goes in here. The code that calls the method doesn't even know that variable exists up to this point. Like before we call the method, there is no variable that will correspond to this address D. And that's why we have to also include the type in here, because there is no prior declaration of this variable. We don't know what to do with it. We have to make the declaration happen here. It's like the reverse case of the ref in that sense. So it's limiting. It's like a ref in that we're talking about a reference. We're talking exclusively about the address in memory, but the flow of information is purely from method to the caller. No information from the caller is accessible to the method, and no data from the caller can be changed by the method. And it's also reverse in the sense that with a ref, the caller has declared and initialized the variable and owns the memory space, the address the variable is stored in, and it will just pass on the address to that existing memory space. But with an out, the method will actually create a variable, but then return. Actually, no, that's the wrong way to put it. I mean, the memory is declared in this part, in this table, so that still holds true. Let's just skip the last statement. Let's just pretend I made a mistake. Actually, I just made a mistake. Let's scrap the last part. It's like a reference, only that we don't know what the value will be until we call the method. The value isn't necessarily initialized when we call the method. And let's make now a check if b equals 0. So in this case, actually no, let's do it differently. If b equals, it's not 0. This is a not. This is the opposite of equals equals. Equals equals will be true if both sides are equal, and exclamation mark equals, that's a not equals, which should be easy to remember. The exclamation mark was a not for booleans. This will be true if b and 0 are not equal. So if it's not 0, we can do a division. And what we do then is simply d equals a divided by b. And we store that value in d. And now we have to return. I forgot to add the bracket here. D equals a divided by b. What we usually do for cases like this, the specific pattern, we return a boolean. Since we return the actual value we're interested in using the out, we are now free to use the return value, the intended return value, for the statement whether or not we were able to do whatever we set out to do. So in this case, we were able to divide, so we can return a true. Let me close this up here. However, if it's not equal to 0, if it is 0, well, let's do what we decided earlier. We just set d to 0, but now we can return a false. So we still return a 0 for the division, just like with a legitimate case where we just get 0. But now we have the additional information that something didn't work. And so when we call this code, well, we now have a variable called diff that will contain the result of the division. We also get a return value from the method itself, which we could use, for example, in an if. Let's this a bit out. If, like that. If this succeeded, we can do some stuff with d. Example, ist gleich equals diff. We could do that. Not necessarily the smart thing to do, but just some code. We could use the variable now, because from this point on, once we call this method, we will have a variable diff. And we can do something else. Also, no clue why I chose exactly this, but a different way to handle the case. If it worked, we use diff, and if it didn't work, we do some other weird thing that's intended for the case where division isn't possible. And because we're not actually dividing anymore, we don't call the method diff. For this specific pattern, we usually call it try something. Because we try to divide. We don't actually know if we will succeed. We can't guarantee it, but we will try. Try diff. Like that. This is the common pattern we have for a lot of existing methods. We'll get to it at some point, and that you probably will use sooner or later when you write your own methods. Where if you can't be certain that something works, you usually have a boolean as an actual return value to tell you if whatever your method was supposed to do worked or not. And if you need any return values, you handle them using something like an out. And just to be clear, this doesn't have to be an out. This could be a ref. You could use a ref perfectly fine. Just rewrite this a bit. We just use a ref in here, and we would need to declare, actually initialize ref, example, like so. This would work. Basically the same result, only in this case, this variable exists before we call the method, and we might overwrite whatever value was in here before. So to make sure that doesn't happen, to make sure that everyone knows this is a one-way street, we use the out variable, the out keyword. Okay, so ref and out, two keywords that let us mess with the internal structure a bit by using actual memory addresses, even though we are not privy to them. We don't see them as programmers. but we can tell the computer to use them in this way. And that way we can optimize a couple of things. If we have a large stack, we can this way cross the boundaries between different method calls in the stack, which can make either the program more efficient in some extreme cases like recursion, or it's just more convenient for the programmer because it lets us just have more output data than the basic method structure, the method design would allow us. And actually that's also where we're gonna stop today. I don't really have anything specific in mind for homework, so I guess you got lucky this time. Maybe if you mention some preparation for next time. We talked about the memory a bit today with the stack, which lets the computer handle memory of varying sizes. So lets the computer, or lets our program use more memory when it needs it, but then frees up memory when it's not needing the memory anymore. So it's always only taking as much memory away from the computer as it actually needs, which is important. And especially in a programming language like C#, memory management and the way it handles memory is a pretty big factor. And I want to... I'm not sure if I should put something ahead already. No, it's better not. The stack exists and is a pretty efficient way to handle memory because we already know exactly when the memory is going to be needed and when it can be freed, and we can rely on that. But you've already seen that there are ways we can break the boundaries a bit. We can reference memory from different sections, from different methods. We can cross these boundaries. So this method could in fact address memory from here. If we just use a reference, for example, a ref that goes in here, which is then passed on here and to here. But with these methods we saw today, with the ref and the out, we can only reference addresses that are further up the stack, that were used by previous method calls. So we never have a case where this method knows an address that is up here. The space that is used is always reserved in one of the upper method calls, in these upper blocks here, and referenced by some method that's further down. So when this piece of memory gets removed, well, all the references to that variable are still valid because the ref that might have been passed on from here to here can still be used. The memory is still there, and the address is still the same memory address as before, the same variable, the same intention behind the data in the memory. Next time we'll see how we can have memory that's going in the opposite direction, where we can actually have memory in here that's referenced in here, kind of. And that requires a whole different way of managing memory and using memory. But it also lets us do some very cool stuff that are the fundamental difference that makes C# a so-called object-oriented language compared to something like C, a basic procedural language. So think about that maybe a bit as your homework. How could we have memory and manage memory when we can't rely on the order in which the stack uses the memory? If we can't rely on the stack anymore, If a method can just reference memory from any different other method, and no matter in which order, how could we store that? What data structure could we use for that? And yeah, that's it for today. See you next time.